This is my favorite equilibrium problem of all time. There's a number of reasons. Um, is because I really like, you got to watch this. I really like this part because one of the things, the big concepts of equilibrium is when there's no net change in the system or the forward reaction and the backward reaction are occurring at the same rate. And see, at 8 hours and 10 minutes, 8 hours and 10 hours, the pressure of the gas is 8.37. It's not changing. So the equilibrium pressure of the gas is 8.37. It also has this initial thing in here. It also is an equilibrium expression that has a solid or liquid in it, and pure liquids and pure solids do not appear in the equilibrium constant. So, okay, I would like to do A very quickly for you. All right, so A, we have this carbon solid plus CO2 gas goes to 2CO gas. And then I'm going to grab a different color. Remember that pure liquids and pure solids do not appear in the equilibrium constant. So Kp is the pressure of the CO gas squared. I generally don't do the parentheses pressure of the CO2 to the first power because this is an implied one and this is a 2 and those are the powers, and that's the first question. And then I'm going to go up here and minimize this so that I can get a new sheet and make sure it's still going because I got burned on that. Yes, it's still going. All right, so then B is a gas law problem. So it's a PV equals nRT. They'll often do that. They'll, especially with Kp, which is equilibrium gas pressure. It's usually a gas law. But B says, what is the number? Calculate the number of moles initially in the container. And if you remember your gas law stuff, N is what we're solving for. So we want to isolate N, which means both sides of the equation have to be divided by RT. So what the College Board would expect to see is that you do the algebra first, which is PV over RT. And then this number, the volume was given in the words, the temperature was given in the words, and the pressure was given in the chart. Let me just take you back. Initial pressure is right here. It's 5 atmospheres. Initial volume is right here. It's 2 liters. And initial temperature is 1,160. And then R is given on the formula sheet. So what is the pressure? 5 atmospheres. What is the volume? 2 liters. R is downstairs, so we have to flip it. So the 0.0, all right, come on, give me a decimal point. 0.08206 atmospheres times liters over mole times K. And then temperature is downstairs too. So the 1,160 K, think that's the temperature. Let me just check. Yeah, it is. Has to go downstairs. And again, I'm going to switch colors. Atmospheres cancels with atmospheres, and liters cancels with liters, and K cancels with K, and nothing cancels with moles, which is awesome because that's what we're solving for. And I've done this problem so much that I know the answer is 0.105 moles. That's a good review of the gas laws. Gas laws are actually pretty easy. My students, we don't do a whole lot of formal review with that because it comes up. Now C has 2 parts, CI, which is actually my favorite because, now guys, there's a number of ways to do this problem, but I just want to do it the way I want to do it. This is overkill, by the way, but I want to make a very important um, point here. Okay, so I'm going to set up an ice chart. I don't really need to set up an ice chart to do this problem, but I really want you to, I'm going to say this a lot of times in the course of this course, that it's all about mole ratio. So here's the deal. We know from the chart that initially this was 5 and this was 0. Now remember, if you're doing Kc, you should put capital M here for molarity. Anytime you're doing Kp, or the gas laws on the AP exam, they always have it in atmospheres. And the reason why is standard atmospheric pressure in atmospheres is 1 atmosphere, and the math is good. Now, so this is cool. Now, let me say this again. You don't really need this to do the problem. There's an easier way to do it, but I want to make this point. If you read the words, it says, very important, I want to go back. It says in CII, um, where are you? Down here. Um, that the equilibrium partial pressure of CO2 is 1.63. The pressure, not the initial pressure, because we know the initial pressure is 5 from the table, but the equilibrium pressure is 1.63. So kind of interesting. This is 1.63. Interesting though, we'll be able to figure this out because this concentration is going to go down and this concentration is going to go up, and I'm going to switch colors. This is an implied one. And this is going to go up twice as fast as this goes down because chemistry is all about mole ratios. And you will pass the test if you have number sense, which most of you do. Okay, now, what does this number have to be? Well, this plus this always gives you this column. So 5.00 minus 1.634, and then 10, borrow 9. 10 minus 3 is 7. 3, this is 3.37. How do I know that? Because 5 plus negative 3.37 is 1.63. Interesting though, this isn't 3.37. This is positive 2 times 3.37. Let me say it again. Chemistry is all about mole ratios, and you got to have some number sense. So what's 3.37 times 2? It's 14, carry the 1, 7, carry nothing. This is 6.74. The question asked for the equilibrium pressure of carbon monoxide. The answer is 6.74 atmospheres. The beauty of this problem and the reason why I love it is, what would the total volume in the container be? What would the total pressure in the container be? Well, the total pressure is the sum of the individual pressures, so the pressure of the CO2 plus the pressure of the CO. And if you add 1.63 and 6.74, you will get 7, carry nothing, 13, carry 8.37 atmospheres. And here's why I love this problem to pieces. Bam! We already knew from the chart that the equilibrium total pressure was 8.37. And so we get awesome, awesome verification that we did it right. Okay, new page for II. Oops, that's not what I wanted to do. I pushed the wrong thing. I need a new page. How do I get a new page? I do not know. Let's just go to the next page. There isn't a next page. What did I do? Okay, let's extend page and see what happens. So then question, so here's question 2, which is, what is the equilibrium expression then? Well, up in A, we figured out that it was the pressure of CO squared over the pressure of CO2 to the first. And we now know that this pressure is 6.74. That needs to be squared, and this pressure is 1.63. And if you do that, you will get 27.9. And remember, KPs are unitless. All right, so all right, I don't know why it's not letting me do a new page, but I'm not going to retype this, so let's just keep extending it. Now, D says, and I might just read this to you, if a suitable solid catalyst were placed in the reaction vessel, would the total pressure of the gases at equilibrium be greater than, less than, or equal to the final total pressure of the gases at equilibrium without the catalyst? Justify your answer. Assume that the volume of a solid catalyst is negligible. What you got to know from last chapter is catalysts, all catalysts do, if you remember, is they make the reaction go faster. That's it. They do not change the reactants. They do not change the products. The only thing that happens is the reaction goes faster. So the total pressure in the container would be equal to the pressure in the container. The total pressure would be equal to the total pressure with and without a catalyst. It doesn't affect the starting points and the ending points. It just affects the reaction mechanism in the middle. So it would be equal to, the total pressure would be equal to the total, that's really bad. The total gas pressure with the catalyst would be equal to the total gas pressure without the catalyst, because catalysts just make the reaction go faster. They do not affect the equilibrium. Okay, what's that? We got to go. Now I got to grab the pointer, and then I got to go down and extend page. All right, I think this, however, is the hardest part of the problem, or hardest part on here, but because it's been a while since we've done this. Okay, E, let me just read the words. It says, in another experiment involving the same reaction, a rigid 2-liter container contains 10 grams of carbon. Who cares? Solid carbon does not enter into the equilibrium, plus CO and CO2, each at a partial pressure of 2.00 atmospheres. Explain if the pressure of the CO2 will increase, decrease, or remain the same. Okay, this is the thing that my students have the most trouble with, is this idea of the reaction quotient. I'm going to call it Q sub P, and it's exactly the same as, it's calculated exactly the same way as the equilibrium constant. It just helps you determine if you're at equilibrium, because if Kp equals Qp, you're at equilibrium. And if Kp is not equal to Qp, you're not at equilibrium, if you remember that. And you know what? I don't memorize that greater than, less than. So the first thing I'm going to do is I'm going to come down here. Sorry, I just wanted to make sure that we were still taping. I'm going to come down here. Actually, I'm not. I'm going to grab the pointer, and then I'm going to come down here and extend the page. So what is QP? Well, Q, pen. Got to grab the pen. QP is equal to 2.00 squared over 2.00, which last time I checked was 4 over 2 was 2. So first question, we're not at equilibrium. Why? Because Q is 2 and K is 27.9. Now, what happens is Q is too small. So in order to, as this progresses towards equilibrium, grab the eraser. I don't know what I'm doing down here. I'm being crazy. So Q is too small. So here's the deal. Now, what is Q? Q is the pressure of the carbon monoxide squared over the pressure of the carbon dioxide to the first power. Now, Q is too small. We need Q to get bigger. Now, there's two ways to make Q bigger. Either you make the numerator get bigger, that makes Q bigger, or you make the denominator get smaller. Either one of these, if you look at this equation, either one of these, so remember, here's the equation. Not that. Either one of, now here's the equation. Plus CO2 gas goes to C2CO gas. All right, you need the pressure of the CO2 to go up, or the pressure of the sorry, you need the pressure of the CO to go up. This needs to get bigger. This needs to get smaller. That's the only way Q can get bigger than 2 and turn into 27.9. And so the question is, will the partial pressure of the CO2 increase, decrease, or remain the same? And obviously it needs to get smaller, which means the pressure of the CO2 will decrease. And I totally believe that all of that work is enough. Now let's look at the scoring guidelines quickly if I still have them up. And I think I do. Okay, so let's just go back to the beginning and just check. There's the equilibrium constant, 1.05 moles. They didn't do it the way I did it, but 6.74. I like my way better, but my way's harder. 27.9. I really like this. Read the words. The total gas pressure of the gases at equilibrium with a catalyst present would be equal to the total pressure of the gases without a catalyst. Although a catalyst would cause the system to reach the same equilibrium state more quickly, it would not affect the extent of the reaction. That means products or reactants, which is determined by the value of Kp. And then finally, because 2 is less than 27.9, the CO2 will decrease as the system approaches equilibrium. And that is it. I'm shutting this down and saving it.